This is a TrendSpark Signal Brief. On July 16, 2026, DARPA and the United States Air Force confirmed that an artificial intelligence agent had controlled a modified F-16 in flight. A human test pilot remained in the cockpit, monitoring the system and able to take control. Officials did not announce an autonomous combat mission or an autonomous weapon release. The flight was real. The fighter was real. The most important question is what the switch between them now makes possible. This is TrendSpark, where we follow the signal behind tomorrow's technology. From the outside, the aircraft looks like a familiar F-16 Fighting Falcon. Inside, it carries the Viper Experimentation and Next Generation Operations Model Autonomy Kit, mercifully shortened to VENOM. DARPA says the kit interfaces with the jet's flight controls, sensors, and mission systems without rewriting its core software. The pilot can toggle between conventional human control and AI control. In the July tests, that meant a software agent was not merely advising the pilot. It was flying the aircraft. The modified aircraft first flew in June to validate that the added hardware, software, and instrumentation operated safely. The program then moved to in-air testing in July, where an AI agent autonomously controlled flight while the pilot remained aboard to monitor both the agent and the mission systems. That distinction matters. Confirmed, an AI agent flew a VENOM-modified F-16. Also confirmed, a human safety pilot remained in the cockpit. Not announced, autonomous combat, autonomous target selection, or an autonomous weapon release. A dramatic headline should not erase those boundaries. Earlier Air Force reporting described additional computing, software, instrumentation, and an auto-throttle that lets the autonomy regulate both thrust and flight control surfaces. Think of VENOM less as a single robot pilot and more as a flying laboratory with a standardized doorway through which different autonomy agents can enter. That doorway may be the real milestone. The earlier X-62A VISTA was a unique experimental aircraft. VENOM is designed as a small fleet of modified operational type F-16s. In earlier air combat evolution tests, AI agents flew the X-62A VISTA in within visual range combat experiments, including dogfight scenarios against a human-piloted aircraft. Those tests showed that machine control could leave simulation and operate inside a real high-performance jet. VENOM asks whether that experimental pipeline can become repeatable and scalable. A reusable fleet can test more agents, more often, under more varied conditions. DARPA's Next Air program is intended to expand toward multiple agents and multi-aircraft live-flight scenarios. That changes the problem from can an AI fly one jet to can several autonomous aircraft coordinate while a human commander understands what they are doing. Speed is the attraction. Air combat compresses observation, prediction, and maneuver into seconds. Software can evaluate possibilities faster than a person can scan every display. But faster decisions are not automatically better decisions, especially when sensors are incomplete, communications are degraded, or an opponent is actively trying to deceive the system.
If the machine reacts in milliseconds, how much time does the human really have to say no? And if the answer is not much, is that still human control?
That is why the phrase human on the loop deserves attention. A person may supervise the system and retain the ability to intervene, but the practical value of that authority depends on warning time, information quality, and system behavior. A switch proves that control can be transferred. It does not, by itself, prove that the human will always recognize the right moment to take it back. Flight autonomy is also not the same thing as weapon authority. An AI can control throttle, attitude, and maneuver without being authorized to select or fire on a target. A separate Air Force collaborative combat aircraft live-fire test in July kept weapon release under human control. That aircraft was not an F-16, and it was not the VENOM test. The distinction is both technical and ethical. Who chooses the objective, who validates the target, who authorizes force, and who remains accountable when the system behaves unexpectedly. The destination is larger than VENOM. The Air Force is developing collaborative combat aircraft intended to fly alongside crewed fighters and operate through open architectures that separate software from specific hardware. In that model, a human pilot may command a team of uncrewed aircraft instead of directly flying every maneuver. Autonomy handles more of the motion. People retain mission intent and, under current test rules, critical authorization. That could extend sensing, distribute risk, and place uncrewed systems in dangerous positions. It could also make supervision more complex precisely when the environment becomes most chaotic. The hard test is not a clean demonstration. It is a damaged sensor, a broken data link, a misleading radar return, an unexpected aircraft, or an adversary that learns how the agent predicts. A trustworthy system must remain predictable enough for its human team, robust enough for contested conditions, and cautious enough to fail safely instead of confidently improvising outside its authority. It must also communicate. A supervisor cannot meaningfully intervene if the machine cannot explain what changed, what it intends to do next, and how urgent the decision has become. So, did an AI fly an F-16? Yes. DARPA and the Air Force say an AI agent controlled a VENOM-modified aircraft in flight with a human pilot monitoring aboard. Did an autonomous fighter independently conduct combat or choose to fire a weapon? No such event was announced. The real breakthrough is the test infrastructure, a repeatable way to put new autonomy into the sky, compare it against reality, and scale from one agent toward coordinated teams. The real challenge is making sure human authority remains operational, not ceremonial, when the machine can act faster than the human can think.
What should matter most? Faster reactions, clearer human control, or proving that the system knows when it should hand the aircraft back?
Tell us in the comments, and tell us what worked, what felt unclear, and what TrendSpark should improve in the next investigation. If this helped separate the confirmed flight from the science fiction version, subscribe to TrendSpark and keep chasing the signal.